Hi, today we're presenting our work on self-supervised learning with iterative clustering for human action videos. The goal here is to learn video representations using self-supervised contrastive learning, specifically for video retrieval and classification tasks. The main contribution of our paper is to use iterative clustering to generate pseudolabels, which can guide a sampling of similar and dissimilar videos during contrastive learning. In many previous works of self-supervised contrastive learning, an image is randomly selected as an anchor, and different augmentations of the same image are treated as similar samples, which are referred to as positives, while all different images are treated as dissimilar samples, aka negatives. As for videos, one of the common strategies is to sample two non-overlapping clips from the same video as similar pair. However, the main drawback of such method is the lack of diversity in the positive training pairs and the need for a large batch of negatives. To address the gap, we propose our method SLIC, which alternates between a clustering stage and a representation learning stage. First, we perform the Finch clustering algorithm in a feature space. Then we use the clustering results as pseudolabels to construct triplets containing an anchor, positive, and a negative. Then we improve the learned representation using triplet loss. Now, let's examine the triplet loss in detail. By minimizing this loss, we're pushing the negative away from the anchor while pulling the positive closer. Using the cluster results as pseudolabels, we can either sample positive clips from the same video or from different videos within the same clusters. We can then sample negative from a different cluster. After sampling the positive clip, we replace the original RGB clip with the optical flow view with a certain probability. This helps the model to learn features that are view invariant. Lastly, we adopt an additional temporal discrimination loss to learn fine-grained motions by constructing a new triplet. We use the same anchor as before and augment the clip to use it positive, then sample a non-overlapping clip from the same or some other similar video as negative. Here we're making sure the same clip with different augmentations should always be closer together in the feature space than any other non-overlapping clips.
To evaluate our method, we first test the performance on video retrieval. As shown in the left column, we sample a set of query clips from the test set of the UCF 101 human action dataset, and for each, we retrieve the top 5 nearest neighbors in the embedding space from the training set, ordered from left to right. While the method is mostly successful in retrieving the video with the correct semantic class, there are cases where classes are confused as a result of similar backgrounds or motions. Here we show the full video retrieval evaluations. On the UCF 101 dataset, SLIC outperforms the next best method by 15% in terms of top 1 retrieval accuracy. On the smaller dataset HMDB51, the improvement is 6%. In addition to our self-supervised pre-training results, we provide results for a baseline called supervised SLIC, which has access to the real class labels when sampling triplets. As expected, having true class information improves retrieval accuracy even further. Next, we evaluate our method on action classification by training a linear classifier on top of the learned embeddings. First, we test the case of freezing the backbone architecture and only fine-tuning the classifier. Under this setting, SLIC provides large improvements in top 1 accuracy. Additionally, we test end-to-end fine-tuning and observe smaller improvements. Lastly, we evaluate SLIC on the larger Kinetics 400 dataset and achieve competitive performance. Prior to the final evaluations, we keep track of 3 metrics during pre-training. The first shown on the left is the retrieval accuracy, which steadily increases throughout training. Next is the NMI, or normalized mutual information, where a higher NMI indicates that the cluster assignments better resemble the true labels. And you can see that this metric increases in conjunction with the retrieval accuracy. Lastly, we monitor the error rates of the positives and negatives sampled from clusters, i.e. the percentage of which did not agree with the true labels. From this plot, it is evident that the false positive rate significantly decreased during pre-training. To verify that the iterative clustering was the primary contributor to these results, we conducted several ablations where we removed different components of our method. Comparing the first and last rows, we see that the iterative clustering results in 22% and 6% improvement on UCF and HMDB video retrieval, respectively. In conclusion, iterative clustering can be used to produce pseudo-labels to sample better positives and negatives for contrastive learning of video representations. This was validated on 2 downstream tasks, video retrieval and action classification, as well as through ablation studies.